Rodrigo Tenorio. I'm a PhD student at the University of the Balearic Islands, and I'm currently visiting Glasgow University. And as Joe just said, today I'm going to present a project developed in collaboration with Rona Molateri, David Keitel, and Alicia Sintes on how to estimate the distribution of the loudest candidate from gravitational wave search. This project is already published as a PhD paper, and we also release an accompanying Python package that is fully open source, and you can have a look at it in GitHub. So after the choir presentation, so let's go down for it. So I'm gonna start talking about gravitational wave searches in general, but disclaimer, this is gonna be about continuous gravitational wave signals in the end, which is something Amy just talked about, so that's gonna be great. So the idea when we look for a gravitational wave is that we are always using, or mostly always using, an approach which is based on much filtering. And the idea is that there's a parameter space in which there may or may not be a signal in the data. And then we parameterize the signal with some parameters, then we place some templates in the parameter space and evaluate the detection statistics on them. And then this detection statistic quite generally is interpreted as a base factor, in the sense that the higher this detection statistic, the more interesting the candidate is, in the sense that it's more inconsistent with noise and more consistent with whatever we consider to be a signal. And so this, in the end, it's natural to focus on the loudest candidates resulting from research. And we can split those candidates into two main sets. We could have this, what I would call clear clear loud candidates, which obviously, in whatever metric you want to express that, correspond to instrumental artifacts or to signals. Yeah, and you can clearly see features in the data that will tell you, yes, this is a, I don't know, we saw an example of this, of scatter noise in the first presentation today, or we can clearly see a chirping signal, shape in which you can say, well, that actually looks like a signal. But then there's another subset of them, which are what I would call marginal outliers, which are at the boundary between what would be a clear signal and what would be an extreme background event. And you can see an example of this in the right-hand side plot. So in the top panel, it's a spectrum of data. And the idea is that there may be a continuous wave signal in there. And if we run a match filtering search, as is shown in the lower panel, you can see that, yes, in the vertical orange line, we put in a signal, and we actually, it's like an extreme value of it, and say, okay, that we are seeing a signal in there. But if you look closely, in this whole template bank we set up, there are a few other not as extreme, so not so strong events, which do not correspond to any signal we have put in there. But because of the fact that this template bank is relatively big, well, they are produced by this background distribution as extreme events. So what is the thing? Typical continuous wave searches evaluate many templates, and that number normally ranges between 1 million templates and 100 quadrillion things here, meaning there's plenty of room to have this sort of things happening in real searches. So if we were able to estimate the distribution of the extreme events produced by the background, we would be able to do with them in a more natural way, and we would be able to stop losing time with them by deeming them inconsistent with signals. So why don't we do this? Well, if we were doing a standard search and using what I would call standard detection statistics, normally we were able to describe the distribution of these statistics on Gaussian noise, and they end up being simple things like, I don't know, chi-square distributions or Gaussian distributions. And if we had a template bank of independent templates, meaning each template is completely uncorrelated with any other template in the bank, we could simply apply the analytical formula and say, okay, the distribution is going to be this one, let's go for it. The problem is that, as everyone is probably aware at this point, real template banks are always correlated, either because data is non-Gaussian and hence different templates in different positions get correlated because of that feature in the data, or because templates are too close to another because we don't want to lose any signals. Hence, if we have a signal, as you can see in this second plot in the middle of the figure, if we have a signal, anything close to that signal is going to give you a big value, which is going to be correlated with the maximum one. Hence, if you look at the bottom panel of this slide, you can see that the distribution that we will get from a correlated template bank is described by this black histogram. And if we try to fit the distribution, assuming this template bank is uncorrelated, which is this blue distribution, we would find out that, well, that it's inconsistent with the actual distribution. So the first thing we did in this work is to realize that, well, we need to deal with that. And the answer is given by extreme value theory, which is a statistical theory from 50 years ago, in which the Fisher-Nelenko theorem was proved. And the idea of this theorem is that the same way you have a central limit theorem for the average of different random variables, you have it for the maximum of different random variables. And quite generally, if you have a technical statistic with a light tail, and you want to you want to get the distribution of the loudest candidate from that from a set of n values, that loudest candidate is going to follow a Gumbel distribution, which is expressed in this in the bottom of this slide. So this is quite generic in the sense that we don't care about the bulk of the distribution to get this result. It's just about having a light enough tail that this is going to apply. And as you can see in the plot, this is represented by this red line, which gives us a much better agreement with the actual distribution than this theoretical approximation, which actually is quite off at this point. So this is one of the main ideas, and is that we can use extreme value theory to overcome the fact that template banks are correlated, and that's great. The other problem is that, well, if we run a search, we will have n templates evaluated, let it be a million templates or a quadrillion templates, whatever you want. But once we have that, we only have one instance of the loudest candidate from that template bank, meaning we cannot fit anything to that, because you cannot fit anything to only one sample. Hence, we need to come up with a method by which we're able to generate multiple samples from a given template bank. Sorry for a second. Sorry. This second key idea I'm presenting here was given 10 years ago in a thesis by Carl Hette. And the idea is that continuous wave searches end up being noise dominated. And that means that if you have a search and you have many templates, you could be able to, in principle, group those batches, those templates into different batches. And each of those batches would be consistent with a different realization of noise, meaning that if you took the maximum of those smaller batches, you would end up with multiple samples from a smaller template bank. Hence, if you are able to describe that distribution, then you could extrapolate that smaller template bank to a bigger template bank and have a proper estimation of the loudest candidate from your search. But at that point, this result from extreme value theory was not that widespread, and hence the approach taken there was to use a non-parametric approximation, specifically a Gaussian KDE, as you can see in the top panel of this figure. And that's great for interpolating things, but the moment you want to extrapolate beyond the support of your data, you will realize that any small artifacts that are in principle unimportant when you start with it are going to be quite important once you try to extrapolate beyond that support. So our method, which uses extreme value theory, uses the proper answer in that sense. And as you can see here, we are able to properly fit the distribution in the top panel with this Gumbel distribution. And once we extrapolate that to the maximum expected value, we get another distribution which is still consistent with the theoretical result and doesn't display any artifacts. But of course, this only proves that our thing is giving us something which looks reasonable, but we do need to demonstrate that that's actually the proper distribution.
And so, yeah, that's your 2-minute warning, Rodrigo.
Great, thank you. So to do that, we do a trial in which we evaluate this detection. We set up a template bank with 8 million templates, and we evaluate it on 900 realizations of Gaussian noise. And then we evaluate the detection statistic on that thing, and we get a proper distribution computed numerically of what would be the maximum over those 8 million templates. And the parameters of that distribution are represented by this black cross in the middle of this plot. And then we apply our method, which we call Destromax, to this in each of the individual realizations. And to compare, we apply the methods using the Gaussian KDE to the same set of realizations. And the results are quite clear. Our results, which are the ones using Gumbel distribution, are precise and accurate estimations of the actual parameters. And one can note that the fact that you're shuffling your data is important in the sense that the more uniform your batches are, the better this method is going to work. And also, as a side note, if you use KDE, as I previously anticipated, you would tend to underestimate the distribution parameters in the sense that KDE, Gaussian KDE, is going to have a shorter tail length. It's going to fall off faster than intended. Hence, whatever extrapolation you do is going to be quite inaccurate. And once we have this, we are able to apply this to other searches or to real data searches. For example, we applied it to this post-glitch continuous wave-like transient gravitational-wave search done on O2 data after the glitch of the Vela pulsar. And in this case, 2 different detection statistics were used, and which are represented by the leftmost histogram in these 2 figures. And in those cases, the idea was that given the samples, you would estimate the loudest of those samples. And that works for the top panel, as you can see here, in the sense that the leftmost histogram is consistent, but it's not consistent with in second panel, in which you use a different detection statistic, the distribution of which is not known. But if you use our method, which is represented by this black histogram, we are still able to come up with a distribution which is consistent with the Gumbel distribution, and hence propagate a result which is supposed to be more consistent with the actual result than any other handcrafted method. And as you can see here, we conclude that the search performance at that point was good enough in the sense that no signals were missed. But the real power of this method is that, as you can see in this quote, continuous wave searchers sometimes resort to use less sensitive statistics just for the sake of not having a proper distribution to describe them and to be able to estimate exactly what's the significance of a candidate. But in our case,
just say that's 10 minutes, so if you can.
Thank you. So I can wrap this up. Basically, by using Destromax, we are able to estimate the distribution of a loudest candidate of a search without knowing the actual distribution of the background by just appealing to extreme value theory. And hence, we can potentially use more sensitive statistics, increasing the sensitivity of a search without having to impact any computing cost. So I'm going to leave you with this summary over here, and I'm happy to take any questions. Thank you.
Thank you very much, Rodrigo. That was great. Let's have a look at the questions. Can't see any right now. I guess I can ask, how do you choose sort of the batch size that you calculate those over? Surely if you vary that, that will have quite a big effect.
Yeah, so we have a plot on that of the paper, and it's actually a good question. So the batch size, you want to have it big enough so that you can fit the distribution. So that means the more batches, the more points you have. And normally across 1,000, 2,000 points, that's going to be fine. But then you have to take into account the fact that you need to have enough templates such that those batches are big enough, such that they actually follow a Gumbel distribution. So if you have, let's say, 1 million templates, you want to have something like 1,000 batches with 1,000 templates. If you have more than that, you can increase the size of your batches. But if you have less than that, you probably want to use a different method because this one is not going to work as properly as it could.
Okay, that makes sense. Thank you. I think we'll move on now to our final speaker. Thank you, Rodrigo. So the final speaker is Thomas Hutchins, who's going to talk to us about gravitational waves from accretion-driven thermal mountains in magnetized neutron stars. So whenever you're ready, take it away.
Sorry, bear with me. It's having a bit of trouble sharing the screen. Sorry, it's asking for permissions. I've really messed this up.
Ooh, permissions.
I didn't expect it to do this.
Lee, do you know if people need permissions for this?
Shouldn't really. I've got you down as a panelist, which means you should be able to share.
Sorry, yeah, it's asking me to quit and reopen. 1 second.